Welcome back. In this segment, we will study two specific divide and conquer algorithms. The first one, called the binary search algorithm that we discussed before, solves the problem of finding the location or index of a particular object inside a sequence of objects. Now, to be more precise, let me remind you of the API for the binary search algorithm that will be more specific about the definition of the problem. So we have two inputs for this problem and for this algorithm. One is an integer sequence of n elements. Now it's important to note that this sequence must be in sorted order. We're going to assume that the terms a sub I are sorted in ascending order. And the second input is an integer which we call the target integer. So to solve this problem, you must return as a solution the index of the target integer inside the input sequence. So the output will be an index between 0 and n minus 1 if the target is indeed found in the sequence. Otherwise, the output of this algorithm will be minus 1 as a convention when the target is not in the sequence. So we discussed this binary search algorithm earlier, but in this version, we're going to write it as a divide and conquer algorithm, which means we need to write it recursively. The prior version of binary search we looked at was not a recursive algorithm, but an iterative algorithm. So let's rewrite it in a recursive fashion that matches the divide and conquer problem-solving paradigm. So let's start the specification of this recursive algorithm with the simplest case, which is the base case of the recursion. If n equals 0, which means the input sequence is empty, it does not contain any integer at all, then we know for sure that the target is not in that input sequence, so we can return minus 1. Now, otherwise, when the sequence is not empty, the first step is to compute m, which is the index approximately of the middle element of the input sequence. Then what we do is we look at that element whose index is m, so this element is a sub m, and we compare it to the target integer. And in particular, if the target integer is less than a sub m, because the input sequence is sorted in ascending order, we know that the target not only is not equal to a sub m, but must appear in the subsequence that is to the left of a sub m in the original sequence, if it appears at all. So all we need to do now is to solve the same problem, a binary search problem, on a smaller sequence, which means the sequence from the beginning a sub 0 all the way to the previous element, the one to the left of a sub m, and that's a sub m minus 1. So we just do a recursive call on that subsequence with the same target, and this recursive call must return the result, which we store in this variable. Now, what happens if this Boolean condition is not true? Well, we have two more cases, so we're going to test for those in the next step. If this is not true, then it could be that the target integer is greater than a sub m. Now, in that case, we also do a recursive call, but we do it on a subsequence that starts right after a sub m. In other words, the subsequence of a sub m plus 1 all the way to the end a sub n minus 1, of course with the same target. And again, this recursive call is going to return a result which we store in the same variable. Notice only one of these recursive calls is going to be executed. And finally, if neither this condition holds nor this one, the only other solution is that target is equal to a sub m, so we don't need to test for it after we failed the previous two tests. We can infer right away that target is equal to a sub m, therefore we found the target and we found its index, which is m. So again, we store the result in its third case in the same variable, which is the index m. And at the end of this body of instructions, we're guaranteed to have the correct result in this variable. And we can just return it. So this is a recursive version of the binary search algorithm. Make sure you're comfortable with it before we move on and discuss how it fits the divide and conquer strategy. Now remember the three steps that any divide and conquer algorithm must execute, namely the divide, conquer, and combine steps. So let's identify those steps in this algorithm. Well, the divide step is performed on this line, since this is where we divide the original input sequence into two approximately equal sequences. Then the conquer step is performed on this line or on that line. Remember, only one of these lines is going to get executed, and each line is similarly a recursive call for solving a similar problem of size approximately half of the original size. So this is where we conquer these easier problems. And remember, the result of the conquer step is a solution for these easier problems. And then the last step is to combine these solutions to produce a final answer to the original problem. And in this case, the combine step is basically skipped because there is no need to combine the solutions to the easier problems because there's only one easier problem. It's either this one or that one. And so there's nothing to combine because the solution to the easier problem is actually a solution to the original problem. But still, it's basically a constant time combine step. And it's right there. We have the three steps in order: divide, conquer, combine. So clearly this binary search algorithm is a divide and conquer algorithm. Now before we move on to the next example, let me point out one thing which I didn't mention before in the case of merge sort, but I'm sure you noticed it, because divide and conquer algorithms are recursive algorithms. Of course, they must have a base case to stop the recursion and to prevent an infinite recursion or an infinite loop. So in this case, this is the base case. And the reason we're guaranteed to hit that base case is because every time through the recursive step, we reduce the size of the sequence, in this case in half. So we're guaranteed eventually to end up with an empty sequence. And of course, the same holds for the merge sort algorithm. So when we give the description of the divide and conquer paradigm, we did not mention the base case, but it was obviously implied. Otherwise, you would have an infinite loop, and that would not be acceptable in any kind of solution, since in this case, the so-called algorithm wouldn't even be an algorithm if it doesn't stop in a finite amount of time with the correct answer. Now, let's consider another example of a divide and conquer algorithm. I'm going to provide the API of this algorithm at the same time as I describe the problem that it solves. So the algorithm is called min-max, and what it does is takes as input an integer sequence and returns a pair of two integers. And as the name indicates, these two integers must be the minimum term in the sequence and the maximum term in the sequence in that order. So the min is first, the max is second. So in this case, we're going to assume that the sequence is not empty, therefore every problem instance has an answer. So the smallest possible problem instance has length 1. So what do we do if n is equal to 1? Well, the sequence only has one term. Therefore, the minimum element in the sequence must be that first term, and the maximum element or term in the sequence must also be that first term. So the min and the max are the same, and therefore we return the pair A0, A0. Now the interesting case is when the sequence contains more than one element. And in this case, we can also use a divide and conquer strategy. So as before, we're going to compute m, the index of the element that's approximately in the middle of the sequence. And then we're going to do two recursive calls. We're going to find the mean and max elements of the sequence to the left and including a sub m. So this is the first half of the input sequence from a sub 0 to a sub m. And the result of this first recursive call will be called mean 1 and max 1. And then, of course, we do a second recursive call on the rest of the input sequence, which is all the elements from a sub n plus 1 to a sub n minus 1. And the result of that recursive call is the pair mean 2 max 2. Now, how do we solve the original problem? Well, what is the minimum term in the whole sequence? Well, it's basically either in the first half or in the second half of the sequence, and therefore all we have to do to find the overall minimum is to take the smallest of these two elements. And similarly, to find the largest element in the overall sequence, we just take the maximum element between those two. And so notice this is the combined step where we build the pair that will be returned, and it's a very simple computation to do here. Take the smallest of two elements, and here takes the largest of two elements. So it should be obvious that this algorithm fits the divide and conquer pattern. Here is the divide step, similar to the two previous examples. Here is the conquer step. Notice this step is similar to the merge sort algorithm because you actually do two recursive calls, not one, like in the binary search example. We store the two results of the easier problems in these variables, and finally we combine those into the final answer to the overall problem, as we just explained. So let's conclude this segment by giving an overview trace of this algorithm on this input sequence, which has, again, 10 elements. So the divide step is going to split the sequence into smaller sequences, in this case these two approximately equal length subsequences. Then the first recursive call is going to find the minimum and maximum values in the first subsequence, namely 1 and 8. Then the second recursive call is going to solve this second subproblem and return the pair 0, 9. So again, this is the divide step, this is the conquer step, and finally we need to combine these two intermediate results into the overall result. So what is the minimum of 1 and 0? Well, the answer is 0. And what is the maximum of 8 and 9? The answer is 9. Therefore, the overall result is 0, 9, where 0 is the minimum value in the sequence and 9 is the largest one. Now notice in this case, it so happens that both the mean and the max were found in the second subsequence, but of course they could have been both in the first subsequence, or one could be in the first subsequence and the other in the second one. This algorithm will work in all of these cases.